Here we have quiz 10. The first question is about an auto cycle. So we have state 1. Well, let's draw it from the piston down at the bottom. This be the top of the cylinder. State 1 with the gas all the way, the piston all the way down. State 2, we've pushed the piston up. So we have 2. State 3, we've added the heat. In state 4, we've dropped the piston back down. The compression ratio is 8.5 to 1. And so we have 8.5 to 1 for our compression ratio. And T1 was 30 degrees C or 303 Kelvin. T2 is equal to T1, assuming an adiabatic and reversible compression. Put work in here. T1 times V1 over V2 to the K minus 1 equals 303 times 8.5 over 1 to the 1.4 minus 1. That's what you'll get if you use the data to get the K. Cp over Cv is K is 1.4. This comes out to a T2 is equal to 713. T3 was given as 1000 degrees C or 1273 Kelvin. So, Q goes in between 2 and 3, and work goes out between 3 and 4. And so this is work out. So the efficiency, thermal efficiency, is equal to work net over Q that was added is equal to, let's see, Cv times, if you do the energy balance between 3 and 4, you'll get Cv times T3 minus T4. And then the work, that's work out, minus work in, and that'll be your energy balance between 1 and 2. Work in comes out to Cv times T2 minus T1, and that's divided by Q, and Q will be your energy balance between 2 and 3. So that'll be Cv times T3 minus T2. The CVs all cancel, and you wind up with just a ratio of temperature differences. You scroll down a little bit. We'll also have to calculate T4. T4 is equal to T3 times 1 over 8.5 to the 0.4. And that T4 came out to 541 Kelvin. So our efficiency then is equal to, see, T3 minus T4, and T3 is 1273 minus 541. All of that minus T2 minus T1, or 713 minus 303, all divided by T3 minus T2, which was 1273 minus 713. And this comes out to 0.575, or approximately 58 So 58% of the heat added is converted to net work in this problem. Now the next thing we'll want to do, question 2, was to find the heat rejected. Well, the heat rejected back to the atmosphere would be taking this energy from the hot gas at 541. So that would be 541 T4, and bringing it back around to the starting point at T1 equals 303. So that Q, call that QL, to the environment would be CV times T4 minus T3. Of course, the other way to get it would be just to subtract the network from the QH. But this is simple enough, so that's equal to 0.718 kilojoules per kilogram Kelvin times, I'm sorry, that's T4 minus T1 here. You're bringing it back to the atmospheric temperature. So that would be times 541 minus 303. And this comes out to approximately 171 kilojoules. Well, this is Kelvin, so the Kelvins cancel. Kilojoules per kilogram. And that takes care of the auto cycle part of this quiz. This is problems 1 and 2 on the auto cycle. Now let's look at our Brayton cycle part of the quiz. You have a turbine and a compressor, and the compressor is driven by a shaft typically that comes from the turbine. So part of the work of the turbine goes to run the compressor, and the remainder you get is, let's call that W net. What I'll do is I'll calculate work of the turbine, subtract work of the compressor to get W net. Let's see, you were told that this was a reversible and adiabatic turbine, and of course you had, so let's insulate our, and a reversible and adiabatic compressor rather. And you also had an adiabatic turbine, so I'll insulate my turbine as well. And you were told, let's see, that QH is equal to 500 kilojoules per kilogram. And let's see, came in with a temperature of 300 Kelvin at state 1. Let's get that in yellow. 300 Kelvin. And you were also, let's see, told that the overall efficiency of the cycle, thermal efficiency, is equal to 37.8%. And let's see, last thing was that the compression ratio was 10 to 1. So P2 over P1 is equal to 10. So if we have a reversible adiabatic compressor, we can get T2 is equal to T1 times 10 to the K minus 1 over K. K is 1.4. Plug that in with T1 equal to 300, and you find that the outlet temperature of the compressor is 579.2 Kelvin. Let's see, an energy balance. Let's do an energy balance from state 2 to state 3. And the QH is 500. So 500 is QN is equal to CP, or the delta H. It's a flowing system now, so you use delta H, and for an ideal gas that's CP delta T. So 500 is QH is equal to CP times T3 minus T2. T2 is 579.2. CP is 1.005. So T2 or make that T3 rather, we're solving for. T3, solving this equation, comes out to 1076.7 Kelvin. Gives us T3. Now, we have T1, 300. We have T2, 579.2. In a gas cycle, you're usually trying to find the temperatures, because if it's an ideal gas, that will indicate the energy content. T3, we have 1076. Now let's calculate T4 if it were an ideal turbine. You're trying to find the efficiency of the turbine. T4 ideal would be equal to T3 times 1 over 10. That would be P4 over P3 to the K minus 1 over K. K is 1.4. Plug in the numbers. You come up with T4 ideal would be 557.7 Kelvin. Okay. Now all we need to do is find what T2 real was. T4 real, and then we can find the actual energy out of the turbine. Well, we know that the thermal efficiency is equal to work net, which is work of the turbine minus work of the compressor, divided by QH, which would be 1.005, that's CP. And I'm going to take that outside. WT would be from 1 to 2, so that would be T2 minus T1 minus, we need the turbine first. Work of the turbine would be T3 minus T4 minus work of the compressor to get our work net, and that would be CP times T2 minus T1. And that's divided by QH, which is 500, giving us 500. We know T3, so I'll put a little check on T3. We know T2. We know T1, put a little check there. And the efficiency, overall efficiency, is equal to 0.378. Solve that equation for T4, and T4 comes out to a little bit of calculation here. T4 comes to 609.4 Kelvin. Okay, so now we need to find the efficiency of the turbine, the isentropic efficiency of the turbine, which I'll do next. Okay. If we have so the efficiency of the turbine then is equal to work that you actually got, work actual, divided by work ideal, which would be equal to CP times T3 minus T4 actual, 1076.7 minus 609.4, divided by CP times 1067.7 minus T4 if it were an ideal turbine, and that was, let's see, up here, 557.7, and that comes out to final answer of 90%. So that takes care of the Brayton cycle. That was kind of an involved problem that required all the steps in solving a Brayton cycle. So that takes care of quiz number 10.